the product, non-degenerate symplectic structures. But since this is already Heisenberg algebra, we have a center in here, taking then the sections, makes an infinite dimensional center. And out of this we form the group algebra and take the representations. And very special representations, namely representations of the Weil algebra or this group C star, the group algebra, or the C star group algebra of the Heisenberg group. H is a Hilbert space and U means the unitary group. And of course we want that the field operators then satisfy the canonical computation relations, and that's what we call a quantization. Of course that's not unique, there is no stone for Neumann theorem out in infinite dimensions, but it doesn't matter. The basic mathematical ingredient is formed by the quaternions. We complement the three-dimensional space by one dimension, and then we have here the multiplication. The multiplication is rather interesting from various points of view. First of all, the scalar valued part of the product, that's the unity, that has the structure of a Minkowski metric. Then of course you multiply the lambdas with the h's, and finally you take the cross product. So to have a cross product, of course we want to have an orientation, and we want to have an orientation on the whole quaternions subducing this one, the one on E. Now Minkowski structures and Minkowski spaces and quaternionic structures are rather closely related. If you have a Minkowski space, an oriented one, you get a quaternionic structure due to that thing here, such that the metric on the quaternionic structure is precise with this one, and vice versa, as I showed you. So the geometric background of the three space is rather interesting. Now, one thing more. I have not mentioned that on the transparency. If you take this cross product and evaluate it along the field vector, suppose you have one, suppose H1 and H2 come out of a plane in 3 space, and then there is one dimension left, perpendicular, say, then the value of the cross product is perpendicular to this plane. And evaluating it along that vector, which is perpendicular to the plane, gives a symplectic structure. So you see symplectic structures in the planes in 3 space, they are all inherited from the quaternions. That's no surprise, but it's very comfortable. So it's not, the symplectic structures are not that strange from the quaternionic point of view. Each direction causes a symplectic structure coming from the quaternionic product in the 4 space. And this has something to do to take a second idempotent in your case. You had one from the Heisenberg structure, and then you took a second one. And in my case, it's the unity of quaternions. Now, if you have a vector in S2, say, a normalized vector, take the orthogonal complement, take again the orthogonal complement, but within the quaternions, that is within the 3 space, the orthogonal complement of the quaternions, that's a complex field. That's a subfield of the quaternions, and it's isomorphic to the complex number. And it is a Clifford algebra, and we know that this even part operates on the odd part. So you see here, in natural way, at each point, that's already the bundle version, you see it from here, at each point you have a very natural action of the complex field coming out directly from the field vectors. Here that's the bundle of complex fields, that's the bundle of complex lines, and that's the unit vector made by the field vector. It might not have the length 1, but this thing, of course, has length 1. And formally, of course, it's clearly the orthogonal complement does not depend on the length of the vector. That's why the complex line bundle associated to the vector field is the same as the one associated to the unit vector field. That's the unit vector field. This similar thing happens with the complex numbers.
Excuse me?
Please.
Can you please try to show the stuff as high up as possible? Because I think we all in the back have a problem to see if you show when it's down there.
I should play only about...
when you talk about certain particular area of your overhead, try to show it as high as possible.
I will shift the transparency. Now the question is, of course, in this little analysis we made so far, how is the influence of the sphere, of the two-sphere, to that whole game? Remember, epsilon is made out of a vector field by squeezing the vectors to length 1. So the values are in the two-sphere. M is the manifold on which you have the vector field. Of course, it's a 3-manifold, say, otherwise it's not that interesting. It has a boundary, possibly the manifold is the whole space, you are an open part of it, so that's a rather varies. But the very interesting part is that the complex line bundle is nothing else but the pullback of the tangent bundle of the sphere. What do I mean with the pullback? Look at this forward here. Think this is the tangent plane of the sphere on the back side. Now, of course, the unit vector points from the back side to here. Of course, I can take out that unit vector and show it outside. Now, I want to pull back this, say, to here. Then I take this board and go to him to this place with that point of the 3-manifold and leave it. Just as the vector points and just as the plane stands orthogonally. That's the pullback. And every complex line is a pullback of a tangent plane. Of course, the same happens with the normal. That means it is the topology of the sphere which plays some role. And of course it depends very much on this map, epsilon. In fact, it will be the mapping degree which helps to classify then later on complex line bundle. The complex line bundle does not tell you anything about the length of the vector, it just tells you the direction of the vector. It's orthogonal. To implement a characteristic part of this bundle, we do the following. At each fiber, we take a circle centered at 0, and the radius has this magnitude. The norm of the length of A of x, and then put into d minus a half. It looks a bit odd, but it gives us in this way a natural, an obvious way of the length of the vector and the natural connection form and all that, namely a natural principal bundle in total. As smaller the circle is,